Okay, so we're gonna finish all of our material this week. Uh, so the last thing I want to cover is Nyquist stability on chapter 10. And because we're actually, I would say 3 or 4 days ahead of schedule, mainly because I cut out chapter 6 or a huge chunk of chapter 6. Uh, what we'll probably do for the last week of class is I'll just have it be turned into office hours. So instead of lecture, I'll just have office hours and in this class, and I'll be online as well. So you can just come in, and if you want to work on homework or have questions, you can just come in. I will probably change office hours for the last week of class as well. So instead of my afternoon office hours, I'll just have this and then probably online office hours only later in the evening because I know some people work and they cannot come into office hours. So we're going to finish everything. And I figured, you know, first week of December, give all of you a break, and I'll give myself a break too. And we'll just jump right into the exam so you get a little bit of rest. And what I'll probably do is we'll finish chapter 10 by I want to say tomorrow, but if not, we'll probably have a half lecture on Wednesday, and if no one comes, that's fine because I'll just record it and upload. I know Thanksgiving's on Thursday, so some people might be traveling the day earlier. That's completely fine. And then probably on Monday of the class, I'll I'll go over classes that UW had just specifically in the mechanical engineering department has offered for control classes and like what each of these classes cover. I'm not going to go over material, but just more of the big picture of what they talk about. So hopefully that'll help you out with class selection, with winter and spring quarter and possibly next year. And then, I mean, Thursday, December 5th is the last day of lecture. So probably Thursday, I mean, I don't think I'll do a review because I already have the chapters 1 through 9 review slides, but I'll just be here for that week. Uh, are there any questions? And if you have any other topics you want to talk about during office hours next week, you can just come in and bring it to me, and we can just talk about it and just do a very casual talk. Okay, so with that out of the way, I've uploaded slides from yesterday. I forgot to change the title. It says frequency response techniques. I'll update the slides again today. So it says Nyquist stability. This is a different set of slides. It's lecture set 11. You'll find most of it in chapter 10, but there is going to be a small section on robust stability that is not in the textbook that I'll talk about. I won't test you on robust stability, but I'll show you how Nyquist stability is somewhat relevant today still. And one thing I would like to go back and revisit probably this week is gain and phase margin and how gain and phase margin relates to Nyquist stability. So I guess the purpose of Nyquist criterion, so the Nyquist stability criterion, it's a graphical technique used to determine the stability of a closed loop system using the open loop system, and it was developed in 1932, before we had modern computers. It accounts for time delays that can cause the closed loop system to become unstable, similar to what Bode plots. Something you cannot observe with checking the location of the poles. The biggest problem with checking the location of the poles is that time delays are not approximated with poles. They are only seen as a phase shift. And in the frequency domain, a time delay is described as a time delay is in the S domain is represented by e to the minus st, where we have a delay of t in the time domain. So when we look at this e to the minus st, if we take the magnitude of it, it's unity gain across all frequencies because you take the magnitude of an exponential, it's that unity. But this will result in a delay, and this can cause instability. And the main reason why is because when you have let's say we have a phase delay of 180 degrees, we flip that sign from +1 to -1. And then when we feed this back, it becomes positive feedback. And that's um, positive feedback with a magnitude of 1 or higher is a guarantee for instability. So you can determine robust stability using Nyquist stability criterion. What I mean by that is with robust stability, how much modeling error can we account for before, or how much guarantee we have with modeling error before the system becomes unstable. So we don't have the perfect model. We can actually use Nyquist stability criterion to determine how much uncertainty we can have. And also finally using this, and this last one it's a little bit dated. So this one's a little dated. Um, because we have modern computers, we can just find the closed loop right hand. We can find the number of closed loop poles using computers, but this is a graphical way of finding the number of closed loop right half plane poles. I think the most important ones are these 2 points. Nyquist stability criterion tells you how much time delay you can have and how much uncertainty you can have with your modeling. Those are the two main points. So I guess with context, just to keep this in context, this method was developed in 1932 before advanced computing. So this is how people determined it back then. We use Nyquist stability criterion to avoid high-ordered computation by hand. When it comes to checking stability, we know the plant, controller, and sensors. So what I mean when we say plant, controller, and sensors, we're talking about the open loop system. So this is if we have let's say we have a closed loop, we have a closed loop system. All closed loop systems has a open loop system where we don't close the feedback loop. This is so on the left side here we have the open loop system, and then when we close the loop, this is called closing the loop. We have our standard system. We're usually given our system on the right, and then back then when people didn't have computers or very powerful computers, they didn't want to calculate this 1 plus GH in the to find the poles. So this is something that we is easy to calculate. This is known, and then this is hard to calculate or hard to hard to find in 1932. And basically, our open loop poles is when GH is equal to infinity. And the closed loop poles is the zeros of 1 plus GH. So when 1 plus GH is equal to 0, that's the closed loop pole for the closed loop transfer function. And also note that the open loop zeros, which is GH, is actually different from the closed loop zeros, which is just G. Because if we look at the numerator, that's our difference. So basically the goal is we want to find the zeros of 1 plus GH, but this can be difficult. Well, and I really don't think it was difficult in 1932. So it's kind of moot now. Um, if GH is high ordered. So the way we want to determine and we can't find the exact values of the zeros of 1 plus GH if we use Nyquist stability criterion. Instead, we're just trying to figure out how many of them are in the right half plane. So we resort to something called mapping. So we resort to mapping. And that's what we are going to do. So we're going to use a technique called mapping, and this is just a trick to determine the number of closed loop poles on the right half plane. So resort to mapping to find number of closed loop poles or the zeros of 1 plus GH in the right half plane. So what we will be, so we're going to talk about mapping now. So we're not going to talk about Nyquist stability yet, but we're going to talk about a technique called mapping. So Nyquist stability criterion uses mapping, and I think it's just better to just show it through to you through an example. But I see it as mapping takes points of S, like points in the S plane, points on the S plane. And when I say S plane, it's just that complex plane where we can just pick any points of S and is plotted on the, here I say G of S plane, but to be more thorough, we should say G of S, H of S plane, because we're trying to include the open loop transfer function or the open loop transfer function. So here we're going to assume that H of S is equal to 1. Then we get G of S, H of S. We're just going to expand this out now, and we get S squared plus 3S plus 2. So I'm going to draw this out now. I'm going to make a table on the left side, and I'm going to make two complex planes on the right side. So here I'm going to have points of S that we're going to evaluate, and then we're going to find those values, G, S, H of S, on the right half plane, or on the right column. We're going to have our S plane first, so points that we are evaluating at. And note that the S plane encompasses the complex plane. And then I'm going to draw a GH plane. I'm going to bias it to have more points on the first quadrant just based off of my example. So I'm going to show quadrant 1 more. We're not going to have any other points in quadrant 2 through 4 in this example, but you can. And we're going to go up to 5, J, and 5 here. So 2, 1, 2. Yep. Oh, and we're gonna have up to 6 points on the real axis. On the S plane, we're gonna have from -2 to 2 for points that I'm gonna plot. Yeah. So this is going to be the G of S, H of S plane. And note that this is also in the complex domain. That's really crooked. Okay. So let's start with the first value, 0. And when I plug S is equal to 0, we just get 2. And this is what mapping is. I put S is equal to 0, and I get 2 right here. And this is called mapping. It's that straightforward. And now I'm going to tell you about the properties of mapping afterwards. But you just pick any values you want. So we can then there's an infinite number of set of values we can pick. So if I pick 1, I get 6 because 1 plus 3 plus 2, that's 6. So then let me plot 1 and then I get 6. And if I choose J, then I get 1 plus 3J. And maybe I just choose 1 plus J and I get 5 plus 5J. So let's map those last 2 points. So if I choose J, positive J, I get 1. So this point, and I go up to 3J. And then if I choose 1 plus J, which is 1 plus J, it's right here. Then I get 5 plus 5J. So I go up to 5, go up to 5J, roughly right there. Get rid of these lines. Yeah, we'll leave it. That is mapping. So that's straightforward. So one thing we want to look at is that, or one property that we like about mapping is that magnitude and phase are preserved through mapping. And what I mean by that is, let's say if we were to find the phase and magnitude of GH at an evaluated point. So let's do this. Let's find the phase. Find the angle of G of S, or let's do G at H at J. And so magnitude of G of J, H of J. So the way we would do it is this. So we go to our, we use our, what we used the magnitude and angle criterion from Routh-Locus. So here we have 2 zeros, one at -2, one at -1. So these are our zeros. And we take the value point here, which is J, and we draw our lines up to here. And this angle I'm gonna call phi1. This angle I'm gonna call phi2. This magnitude I'm gonna call M1. And this magnitude I'm gonna call, sorry, I'm running low on space, let me flip these. This is going to be M1, that's going to be M2. So all we do is we just find the magnitude like we did in chapter 8. Kind of similar to what we did on the Routh-Locus. But this time we don't need to check if the points are on the Routh-Locus. We're just trying to find the magnitude and phase. So then we get this. We get magnitude of G of J, H of J is equal to magnitude of, or actually the magnitude of S of J plus 1 times J plus 2. And that's going to be equal to the magnitude of M1 times the magnitude of M2, which is just equal to 3.16. So we're just using the S-plane to find our magnitude right now. And then when we do the angle, it's going to be something similar to this, where we have the angle of G of J, h of j is equal to, the sum of the angles of the zeros minus the sum of the angle of the poles, which is equal to phi1 plus phi2, and we have no poles, where phi1 is going to be equal to arctan of, here we have 1 over, let's see, it's going to be our evaluated point, which is j, minus our zero location, so 1, because it's minus minus 1. And then phi2 is going to be equal to arctan of 1 over 0 minus minus 2. I actually don't have those numbers calculated, but I think it would be, so this is 45 degrees. I don't have this number calculated. I think it's 26.6 degrees. I actually just have the final number, which is 71.6 degrees. So I think that adds up to 76.6 degrees. So this is nothing new. But then if I were to do it on the GH plane, basically, I'm going to call this magnitude M3 and this angle V3. This is equal to V3, and this is equal to M3. I guess a better way of saying this, because M's are implied to be magnitudes, so it'd just be M1 times M2. So this is how mapping preserves phase and magnitude information. Because because on the S plane, what we're doing is we're taking the individual points from each pole and zero to our evaluated point, multiplying the magnitudes and multiplying by the magnitudes of the zeros divided by the magnitudes of the poles. And then for the angle, we do sum of the angle of the zeros minus sum of the angle of the poles. When we map this, we don't have to evaluate all those individual points. We're just evaluating the point from the origin to the new mapped location. We get that magnitude and we get that phase, and that's going to be the same. So phi3 is equal to phi1 plus phi2, and M3 here is equal to M1 times M2. So these are the same. So this preserved. We preserve this information. Any questions? So this is what mapping is. So mapping preserves phase vector information. So in other words, the magnitude and angle information are preserved. And I guess steps for mapping are written out here. Mapping a single point. So you just pick a point S, which is a real and an imaginary point. So you can pick a real or imaginary or a complex point on the S plane to map onto the G of S plane. I really need to update this. It should be the GH plane. And usually H is equal to 1. We draw our phasors from the poles and zeros to that point on the S plane. So basically, I just draw this green line to that point. And then the magnitude of the phasor on the GS plane is found by multiplying the magnitude of the zeros dividing it by the multiplied magnitudes of the poles evaluated at that point. The phase is found by adding the sum of the zero angles and subtracting by the sum of the pole angles. And then we repeat steps 1 through 4 to map each individual point. So we can do another example on this, where if we have a pole and zero, This one should be pretty straightforward. So we have our S plane, and we're trying to map it to 2J. So and draw a map that's biased to the quadrant number 2. Then we have our G of S, H of S plane. It's going biased towards quadrant 1 because that's where it maps to. I already have the value. It's going to map to 0.25 and 0.75. So I have 0.25J, 0.75. Then here we're mapping to 2J, and then we have a pole at -1 and a 0, or a pole at -2 and a 0 at -1. So I'm going to draw my 0 right here, my pole right there, map point right there. And then what I'm going to do is I'm going to draw my phasors. Call this M1. Let me call this phi. Let me call this theta because that's our notation we've been using for our poles and zeros. And let me call this M2. So basically when we plug in 2J, then we get this value of 1 plus 2J divided by 2 plus 2J. And then we just multiply the top and bottom by the conjugate of the denominator, which is 2 minus 2J, to get rid of the imaginary term in the bottom. And then I end up getting this value 1/8 times 6 plus 2J, which is equal to 0.75 plus 0.25J. So that's where I get this map point right here. And my phasor going to this point. Call this M3. I'm gonna call this psi. So then phi1 is equal to, or phi is equal to arctan of, here we can see it's our evaluated point subtracted by our 0 location, which is going to be 0 minus -1, so 2/1, which is equal to 63.4 degrees. Theta is equal to arctan of 0 minus -2, which is 2, which is just equal to 45 degrees. And then, so using this, we can determine the angle. We get angle of G of that, G of 2J, H of 2J is equal to 63.4 minus 45, which is equal to 18.4 degrees. The magnitude of M1. So actually, let's do this. The magnitude of G of S, G of 2J, H of 2J is equal to the magnitude of the zeros divided by the magnitude of the product of the poles, which is going to be M1 over M2, which is going to be equal to the magnitude of 1 plus 2J divided by 2 plus 2J, which is equal to square root of 5 divided by square root of 8, which is equal to 0.79. All right. So if we were to check that, psi is equal to arctan of 0.25 divided by 0.75, which is equal to 18.4 degrees. And magnitude of M3 is equal to magnitude of 0.75 plus 0.25 J. And we get 0.79. All right, so it's pretty straightforward example, but that's all to do one point. And with the Nyquist stability criterion, we're actually taking an infinite number of points, and that's not really feasible time-wise. So what with Nyquist stability criterion, when we're doing mapping, there's only going to be three main points we're going to be evaluating for, and I'll show that soon. Uh, I will want to talk about mapping shapes. So here are some general mapping properties. So if I were to read this chart here, like figure A, B, C, D, and E, so there are five figures here. The left chart is my S plane, as you can see here. And then on my right chart, it's the F plane, and they give you the function F. And they give you, you can see what it looks like when we evaluate all of these points along this contour. Basically, these are the points we're evaluating or mapping from. And we map it to this plane here, which is shown denoted by this circle here. Notice that these are closed contours. Closed contours. And so these are just some mapping properties where let's say now we have a pole, and then we have the closed contour on the right. Note that there's an arrow here to note the encirclement direction, arrow for encirclement direction. And this is important. So you can see here we also have an arrow right there too. So the encirclement direction for the contour will also, so it's either going to be clockwise or counterclockwise. And one thing I want you to note is that for figures C, D, and E, what happens when you map a zero within the contour? So here we have a encirclement of zero. So encirclement of a zero. And you see here, the origin is encircled. An encirclement of a zero encircles the origin on the F plane. So you see how the origin is encircled when you encircle zero. So it's the same with the pole. When we encircle a pole, we also encircle the origin as well. And this is a pretty important property for Nyquist stability. All right, but then this is where things also get weird, is if we actually encircle a pole and a zero, there is no origin encirclement. So no origin encirclement. And that's only when you encircle a equal number of poles and zeros. No origin encirclement for an equal number of poles, number of P and zeros. So poles and zeros. So if our contour encircles a pole and a zero, or let's say it encircles three poles and three zeros, then we will no longer encircle the origin. But let's say we have three poles encircled and one zero encircled, then maybe we have a pole here and a pole here. Then you'll actually have, I do think you will encircle the zero again. Or sorry, if I have a pole here and a pole like that, then we'll have encirclement in the origin. One last thing I want you to note is the encirclement direction. So here, this is clockwise. And then here we have a clockwise encirclement. Here we have a clockwise encirclement. And then we have a counterclockwise encirclement. So I want to make a note about the encirclement direction as well. And this isn't as important, but this is a note on encirclement direction. So if we look at figure D, so D has a clockwise encirclement. Which is on the S plane, but a counterclockwise encirclement in the F plane. And this is only when you're encircling a pole within your contour in the F plane. And the reason why is because when we look at so why does this occur? So why? If we look at the angle of F, it's going to be the sum of the angles of the zeros minus sum of the angle of the poles, which ends up just being the negative angle of the negative sum of the pole angles. So because of this negative number, the encirclement is going to go opposite of your contour. So when we go clockwise, it's going to go opposite because the angle's negative now. I've only taught this once, which was in 2021, and I actually had people draw this out, or I drew this out in class, and this is why we're a week ahead. I hate drawing these out. Anyway, are there any questions? It's a lot of graphs to draw out. So this is some general mapping properties. So now we're going to jump back to the Nyquist stability criterion. So Nyquist stability criterion uses mapping. So it basically Nyquist stability criterion takes the following points on the S plane and maps it to the GH plane. So notice we're looking at the S plane again. And basically what we're doing is we're taking all of these individual points on this contour, and it looks like a half circle. Infinite number of points, and we're mapping it to the GH plane. So this has a radius of infinity. So this is encompassing the whole right half plane of the complex domain. So basically all points of S are on the boundary, on this boundary here that I have. And this contour contains all right half plane poles, and specifically it's going to be open loop poles and zeros. So we have any open loop poles and zeros, they're going to be inside this contour. Left half plane poles and zeros are not contained within this contour. And we want to basically map it to the GH plane. So we map to the G of S, H of S plane. Okay, so this relates to a theorem called the Cauchy's theorem, where if a contour S in the S plane encircles M zeros and N poles of G and H, and does not pass through any poles or zero of GH. So if it, let's say I have a pole here, like on the imaginary axis, that means the contour passes through it. When we will have a special case for how we deal with that. But we're going to ignore that for now. And the transversal is the clockwise direction along the contour. So meaning that we're going this direction. This is clockwise. Then the corresponding contour in the GH plane encircles the origin of the GH plane n times. Okay, so it's a lot of words, but I think examples and equations are easier to understand than a paragraph. Basically, this is what Cauchy's theorem states. Here, the way we read this is we have these two equations and basically this CCW will tell you the direction of the encirclement, the number of encirclements in either the counterclockwise or the clockwise direction. Now, this Z here is the number of closed loop poles inside that contour. When I say contour, it's going to be that like that infinitely big half circle contour. We want this to be 0. We want Z equal to 0 for stability. Because if Z is any number, it means that we have Z number of closed loop poles in the right half plane, because that contour is saying this contour is the right half plane. It encompasses the right half plane. So for Z to be equal to 0, we need P to equal to N. N meaning NCCW or NCW or NCW. So P here stands for the number of open loop poles inside the contour. And the open loop poles is something that we can find relatively easily. And then NCCW is the number of counterclockwise rotations about -1, and NCW is number of clockwise rotations about -1. And then here's a notation about when these values are, when P is less than Z and P is greater than Z. And it tells you the encirclement direction. Usually we don't have to draw the contour, but I usually draw the contour in the clockwise direction. I'm not going to be mean and draw the contour in the counterclockwise direction for the exam. I'm just going to have it clockwise direction. So this is basically the Nyquist stability criterion. And then we're looking at encirclements about -1. And I'm going to talk more about why we look at -1, but let me just give you the steps first. So basically, you don't have to find, we just need to find key points. And our starting point is where we let S is equal to J omega, where omega is equal to 0. And we find that point. We map that point. And then we determine the imaginary axis crossing on the GS plane, where we let S is equal to J omega, and we want to solve for the imaginary part with real part specifically equal to 0. And that's where the crossing at the imaginary axis occurs at omega. Then we determine the real axis crossing on the GS plane by letting the imaginary part equal to 0 and having only the real yeah, we only look at the real component. And then we look for the midpoint by sweeping the omega from 0 to infinity. And then once we get the midpoint, we actually are done drawing our Nyquist plot. We just reflect it about the real axis because it's symmetric about the real axis. Again, we'll go through an example. It'll make more sense. And I'm going to just end it on this slide and show you on MATLAB why mapping is useful. So we are mapping the plane GH, but are interested in the mapping of GH plus 1. And the reason why is because we're looking at the closed loop transfer function. So the closed loop transfer function is this. G over 1 plus GH. But we're mapping GH. And basically we shift the origin to -1 because whatever we map, when we just add 1 plus GH, we shift the whole plot to the right by 1. So our new origin is -1. And this is why we look at encirclements at -1. And that's what Cauchy's theorem was talking about. Or that equation I was looking at, why we look at encirclements around -1. So the stability of the system is based on the closed poles, which is the zeros of 1 plus GH. So we look at the number of circlements and the direction of the encirclements around the -1 in the Nyquist plot, and we use that to determine stability. And the closed loop system is stable if and only if, for the contour, the number of counterclockwise encirclements about -1 is equal to the number of positive real open loop poles. In other words, n is equal to -p. So here, this is how we analyze the Nyquist plot. And for next class, I'll show you how to draw the Nyquist plot for a system with only poles, and then we're going to look at one with poles and zeros. And then basically for the homework, the final homework, I'll probably just add 1 or 2 Nyquist plotting questions where you have to plot it by hand, but then you can use MATLAB to check if your plots are good. I'm going to show you on MATLAB what it looks like if I were to plot, use Nyquist plot. So here I have a generic open loop transfer function called GH. I'll upload this. Okay. And in the blue is the plot of GH, and in the orange is the Nyquist plot of GH plus 1. And they're identical plots. The only difference is when I add 1, I'm adding 1 to the real value. So everything is just shifted over by +1. So even though GH plus 1 will have different phase and magnitude information, the shape of this plot remains exactly the same, and it only moves over by 1. And then now you can see here, we're looking at encirclements around -1. And the way we read this plot is here, we can see in Nyquist plot of GH plus 1, we're touching the encirclement. And that's actually a case where we'll have marginal stability. When we have encirclement, it usually is unstable, but we need to look at the number of open loop poles where we have in the right half plane as well. So anyway, this is why Nyquist stability is useful. It's for this reason, where we can when we plot it, even though phase information changes, the shape remains the same. So we'll pick this back up tomorrow and probably finish chapter 10 and basically the whole course tomorrow. All right, thank you.